Okay, last class we have discussed about this transmission gates, and then we have discussed about the non-ideal characteristics of CMOS. Okay. Normally, if a CMOS transistor, in that if NMOS is on, we will take as closed circuit, if it is off, we will take as open circuit, but practically there will be some resistance. Okay. So, you have shown the resistance equivalent model of NMOS and PMOS, and I have given the expressions for the resistance. Okay. Now, today we will discuss about the delay times. In order to find out the speed of the CMOS circuits. So, there are three important delay times are there. One is called rise time, fall time, and propagation delay. So, these three will decide the speed of the circuit. So, in order to find out this rise time, we have to consider a CMOS circuit. We will take a simple CMOS inverter. So, what is the rise time of CMOS inverter? So, once if you understand this rise time derivation of the CMOS inverter, you can do it for any CMOS circuits. Okay. So, rise time is normally defined as the time taken to change the output from %10% to 90% of final value. For example, if I take this CMOS inverter, this is ground and this is VDD, this is PMOS transistor, this is NMOS transistor, this is V in, this is V out. So, this is a function of time. Let us assume that here we have some CL. So, V out is function of time. Okay. So, I will write as V out of t. So, in order to find out the rise time, the output has to change from 10 to 90%, means the output has to change from logic 0 to logic 1. Okay. Rise time is TR, TR is also equivalent to T low to high. So, low to high transition time, L stands for low, H stands for high. So, in order to find out this, initially we will assume that V out of 0 at 0 time is equal to 0. Okay. Now, in order to change the output from 0 to VDD, so the input you have to apply as, let input V in is equal to 0. Then what happens? Implies this is PMOS and this is NMOS. So, PMOS is on and NMOS is off. So, in the previous analysis we have assumed that on means short circuit and off means open circuit, that is the ideal case. Okay. Whereas, in practical case, as I have discussed in the earlier lecture, so there will be a resistance. So, now the equivalent circuit here will be something like this VDD, here we have the on resistance, whereas the lower part is open circuited. So, here we are going to take the output V out. So, this capacitance will be now C out, which is sum of CL plus the capacitance of the FET, this is RP. Now, the output was initially 0, now it will charge towards VDD. This is the charging path. With the time constant of tau p, we will call as, this is RP into C out. This is the time at which it will charges. Now, if I draw the output waveform, as a function of time, E out of t. So, initially 0, after that it will rises exponentially. Okay. So, this will be 0, it will goes to VDD. So, you see the steady state value is VDD, in finite time it will goes to VDD. So, initially it was 0 at t is equal to 0. Now, to define the rise time, we are going to define 2 points, one is 90%, if I call this one as t1 time, this is 0.9 VDD, which is 90% of the final value, and here somewhere we have 10% of VDD, this is 0.1 VDD, and if I call this time as t1, this as say t2. Then this particular time from here to here is called rise time, TR. So, TR can be defined as T2 minus T1. So, this can be easily write the mathematical expression for this V out as a function of time is V out of time, I am not writing function of t, it is understood. So, this can be written as VDD times 1 minus e raised to the power of minus t by tau p, where tau p is RP C out. This is clear that when t is equal to infinity, e raised to the power of minus infinity is 0, 1 minus this one. So, at infinity, when t reaches to infinity, this will reach to VDD. When t is equal to 0, e raised to the power of 0 is 1, 1 minus 1 0. So, output is 0 here. So, this exponentially it will rises. Okay. So, to derive this expression for the rise time, set t is equal to t1, output VDD will be, output V out will be 0.9 VDD, 0.1 VDD, t is equal to t1, 0.1 VDD. So, if you substitute this here, 0.1 VDD is equal to VDD into 1 minus e raised to the power of minus t becomes t1 divided by tau p. So, what is t1 expression? VDD get cancelled. So, 0.1 is equal to 1 minus e raised to the power of minus t1 by tau p, and if I take this 0.1 to that side, this to this, implies e raised to the power of minus t1 by tau p is equal to 0.9. If we take logarithm on both sides, minus T1 by tau p is equal to logarithm to the base 2, 0.9. So, T1 is equal to minus tau p ln 0.9. Similarly, to get T2, this is the case at T is equal to T1, this is the expression. Similarly, at T is equal to T2, V out is equal to 0.9 VDD. If you do in a similar manner, you will get T2 as minus tau p ln 0.1. You can easily see that this will be 0.9. So, if we subtract from 1, it will be 0.1. Okay. Therefore, what is TR is equal to T2 minus T1, this is equal to minus of tau p is also common, minus tau p is common, ln of T2 is 0.1 minus ln 0.9. This is equal to ln A minus ln B is ln A by B ln B. And if I take this minus sign, this division will be reverses. This is equal to tau p ln 0.9 by 0.1. This minus sign I have removed, I have changed this order. This is equal to tau p ln 9. Ln 9 is approximately equal to 2.2. So, this is approximately equal to 2.2 tau p. So, this is the rise time of CMOS inverter. Similarly, to find out the fall time, fall time is defined as the time taken to change from 90% to 10%. This is reverse of that of rise time. Okay. So, to change from 90% to 10%, initially we will assume that V out of t is equal to or 0, V out of 0 is equal to VDD. Now, I want to make this to 0. So, in order to get to 0, we have to make let input is equal to VDD. When input is high, implies NMOS is on, PMOS is off. So, what will be equivalent circuit? PMOS is off means off resistance is infinite. So, it will be open circuited. So, the only lower part will be there. So, this is the capacitance, this is the output point, V out. This is ground, this will be C out, this is Rn. Now, this is the discharging path. So, the output was initially at VDD, now it will discharge as to 0 with a time constant of tau n is equal to Rn C out. So, if you draw the output characteristics versus time, so initially output was at VDD, then it will changes to So, this is VDD and 90% of this one is this 0.9 VDD, we call this as some time, and 0.1 of VDD is somewhere here. This you call as T2, this you call as T1. Then fall time is T2 minus T1. This also can be called as the time to change from high to low. So, what will be the expression for this one? So, you can derive the expression in a similar way to that of rise time. So, this V out expression will be as a function of time is VDD into 1 minus will not be there, simply e raised to the power of minus t by tau n. Because at t is equal to 0, what is the value? T is equal to 0, e raised to the power of 0 is 1 VDD. So, this is VDD. At t is equal to infinity, 0. This will reaches to 0 at infinity. Okay. So, we can derive in a similar manner. The TF expression also will get approximately as 2.2 tau n. Yeah, both the expressions are same, the only difference is in time constant. So, the time constant of rise time, fall times will be different. Okay. Now, once if you know this rise time and fall time, then the frequency at which the MOSFET can operate is given as 1 by Tf plus Tr. This is the frequency at which the MOSFET can operate. So, in order to operate the MOSFET at higher speeds, higher frequencies, if you want the more value, this should be less. So, means the time constant should be less. If time constant is less, speed of the CMOS circuit is more. Okay. So, in order to represent, there is another parameter called propagation delay. So, these three can be represented using some syntax in Verilog code. Okay. That is why I am discussing this. If pulse type of the input is applied, say this is 0, this is 1, again this is 0, if this is the input as a function of time, then what will be the output? Of the inverter. So, when the input is 0, output will be VDD. So, this is VDD, up to here this is VDD. When input is 1, output will be 0, but that 0 will comes slowly, because this is the practical case. So, this will come like this. So, like this, then again it will rises, it will come with some slope, then again it will rises to VDD, because here it is 0, this will be VDD again. So, somewhere here the 50% of VDD is there, 0.5 VDD. This difference from this is the point where this VDD is there, and this is the point where it reaches the 50%. So, this gap is called as propagation delay of rise time, and similarly this 50%, this value, and where it reaches to the full value VDD. This is 50% and here it reaches to the VDD. So, this value is called Tp fault time. Then Tp is called average of Tpr plus Tpd Tpf divided by 2. Now, if we derive the expression for this Tpr and Tpf in a similar way to that of the rise time and fall time, we will get this expression as Tpr is approximately equal to 0.7 times tau p. Tpf is equal to, so the expression for the rise time is p and this one is 0.7 times tau n. So, therefore, this will be 0.35 times sum of the time constant of n mass, time constant of p mass. This is expression for this total propagation delay. Now, we have 3 primitives. So, earlier we have discussed about the 3 primitives in ideal case, okay, that we have discussed as n mass. The general structure is some n1 out data control, whereas in non-ideal case, that is called resistive switches. This is the ideal switch, this is corresponding to ideal switch. If I take the resistive switch, this will be, we will get Rn mass, N1 out data control. The only difference between n mass and Rn mass is, so here we are going to represent with the resistive type of equivalent circuit, okay. Whereas in case of just a mean n mass, this will act as a short circuit, that is the difference. Now, in order to represent the delay, normally you can represent delays. Similarly, you can write for this p mass also. We have similarly we have p mass is for ideal, whereas R p mass is for resistive. We have similarly R c mass, P1 out data CTRL control, and C mass is normally will get TG transmission gate, we have discussed in the earlier lecture also. So, this will be out data, we have 2 controls, control underscore P, control underscore N. Okay. So, these are the 3 primitives for the resistive switches. Now, in order to represent this rise time, fall time and propagation delay, we can use a pound type of the symbol. Okay. So, if I write say Rn mass, pound type of the symbol, and if represent within the parenthesis some 2, then the remaining is same, out data control. This is one example. If you have only one value, then this represents propagation delay. On the other hand, if you have something like R P mass, and if you have 2 values, if you have something like 3 4 P1 out data control. So, these 2 values represents, the first one is rise time and then second one is fall time. Sometimes you can represent 3 values also. Another example, see example 1, where we have only one value, This is example 2, we have two values. Example 3, we can have three values, say R CMOS pound symbol, we have 344. We have some name of this, some TG out comma data control underscore n control underscore p. So, here these three value represents, this is rise time, fall time, then off time. This is how we can represent this rise time, fall time and propagation delays in case of CMOS circuits. So, till now we have discussed about the various primitives of switch level modeling. So, one is simply NMOS, RNMOS, PMOS, RPMOS, CMOS, RCMOS, and then we have supply 0, supply 1. Okay. So, these are the various primitives that we have discussed till now. So, there are some more primitives such as pull up and pull down. So, what are these pull up and pull down? As I have discussed in the earlier lecture. Okay. So, when the output charges, if I take this CMOS inverter, so it will charge through this PMOS which is connected to VDD, this capacitor, C out, this output will charges to this one. So, this resistance is called pull up resistor. So, in order to represent this pull up and pull down, normally we can define this as pull up. If I represent with out 1, this will gives high outputs. So, this will be something like, here we have connected high and there will be resistance. So, this will be connected, this is 1, logic 1, this is in a block box. If you have this in a block box, and if we take this point, if I write this as out underscore 1, if I write simply pull up out 1, this will give high output. Okay. Similarly, we have pull down out, so which will be something like, if we take output here and if you have resistance and if I connect to ground, this if I take as a block box, this will be out 0. If I write pull down out 0, so this will means the output will gives low value. The upper circuitry here, I will assume that this is open circuit type of thing. Okay. Similarly, here the lower circuit will be something like open circuit. Okay. So, if I connect this in a complete circuit, so depends upon this upper circuitry of this and lower circuitry of this output will varies. This can be either 0 or 1. So, simply I will use pull up out or pull down out. Instead of 0 and 1, I will write pull up out and pull down out. Okay. This will be better understood if I consider an example. Let us take a 3 input NMOS NOR gate. You can also call it as pseudo NMOS. Here we are not going to use p type MOSFETs, because this p type MOSFETs, the equivalent circuit will be represented by the pull up resistance. Okay. So, the circuitry for this one will be, this is pull up resistance, then we have 3 input NOR gate, this we have to connect to the ground, this one will be connected, this will be in block box. So, here we are going to take the output, this is pull up out, you can also call it just simply output, V out. This is NMOS, if you have three inputs A, B, C. Here thing is, as long as this 3 NMOS transistor, if I call this one as N1, N2, N3, if all NMOS transistors N1, N2 and N3 are off, means that is A is equal to B is equal to C is equal to 0 or low. Then what happens? This will be open circuited, this entire circuit will be open circuited, this output will be connected to this one. Okay. So, this will be, because this is pull up resistance, the output will becomes, output will be pull up to 1, output will be 1. Okay. So, if any one of this input is on, so what will be equivalent circuit? Let A is equal to on, B, C is equal to 0. Then what will be equivalent circuit? This will be on, so this will have some resistance, this will have some resistance of this network, this is pull up resistance. So, the equivalent circuit will be, this is 1, this is pull up resistance, now this point here also will be having some resistance connected to ground, this is where you are taking the output. Okay. So, in this case what is V out? V out will be 1, because this V out will be pulled up, okay. Whereas, in this case V out will be, so this is R n and this is some pull up resistance, okay, say some R p. This is not p type, if I use the p type then equivalent circuit you can write this one, but this is actually pseudo NMOS, only NMOS transistors we are using, there is no PMOS transistors here. Okay. So, here what will be the output now? So, here also there is some resistance, here also some resistance. Okay. So, normally we will choose this pull up resistance such that this is less than, Rp is less than the on resistance of NMOS. Okay. So, that the output will becomes 0, that is what the operation is required for the NOR gate. Okay. So, we will choose this pull up resistance such that Rp is less than Rn. So, in that case, so the one which dominates, that will comes to the output. Okay. Rn dominates, Rn is connected to ground, so output becomes 0. Okay. So, this is how you can pull up or pull down this network, and the Verilog code for this circuit is, we can write the Verilog code as module, we take 3 underscore NOR gate, some name, the inputs are, output is only V out, inputs are A, B, C, output V out, input A, B, C. So, an important point that we have to remember here is, no need to define the supply 1, only supply 0 ground is enough. And no wires are required because these 3 points are connected to V out, these 3 are connected to ground. Okay. Then you can define NMOS. You can also write down R NMOS also, because this is not ideal. N1, what is the output and input? Output, data, and then control. Okay. Control is A, output is drain, source, gate, output is V out, data is ground, control is A. Similarly, Rn, mass, N2, V out, ground, and V. Similarly, Rn mass, N3, V out, ground, and C. Then the output will be pull up, out. So, this out will be 1 if all these 3 inputs are zeros, otherwise the output will be 0. Okay. End module. So, in a similar manner you can explain about pull down also. Okay. I have explained about the pull up with example. So, in a similar manner we can use pull down also, pull down out. Okay. So, these are the other 2 primitives. Okay. Then we have the bidirectional switches also. So, till now we have discussed about the unidirectional, the current flows from drain to source only. Okay. So, we can have bidirectional switches also. So, the primitives for these bidirectional switches are tran if 0, tran if 1. Of course, this you can use with OR also. So, that we can use for the idea the resistive type. This is without this is ideal switches, we can have 3 resistive switches also, bidirectional resistive switches. R tran if 0, R tran if 1. So, there are totally 6 primitives on bidirectional switches. So, as the name implies, so the data can flow from input to output or output to input. If you have this S1 and if you have a switch, this is S2. Data can flow from S1 to S2 or S2 to S1, depends upon the position of the switch. Okay. So, in case of tran, directly switch is closed, data flow can flow from both the directions. Trans if 0, so this switch will be closed if control signal is 0, there will be control signal here. Okay. So, this will be something like just a simple switch, we have some simple switch. This is the symbol for the tran with input and output. Whenever you write this tran, this switch will be closes. So, the data can flow from input to output or output to input. Whereas, in this case tran 0 and tran 1, tran if 0, we can have a switch. This switch will be closes whenever if there is a control signal, which is, if control signal is 0, switch will be closed. So, the data will flow from input to output or output to input. As for tran 1, is reverse. There is a control signal without any bubble. If control signal is 1, then there will be a data transfer, otherwise this switch will be open circuited. So, instead of open circuit and short circuit, if you have resistance, then we will use this R tran if 0, R tran if 1. So, there are 3 some bidirectional switches and there are some 6 primitives related to bidirectional switches. Okay. So, there are some signal strengths. So, we can have totally 8 different signal strengths. Okay. So, as we know that in case of resistive switches, here the signal level is something like S1, signal level is S2. Similarly, if I pass this S2 to some other resistance S3, then in terms of this signal strength, S1 is greater than, S2 is greater than S3, because S1 corresponds to some voltage level, there will be some voltage drop across this resistance. So, S2 is less than S1. So, after that there will be some more voltage drop. So, S3 is less than S2 and so on. So, when the signal propagates through the resistances, the signal strength will decreases because of the voltage drop across the resistances. Okay. So, totally we can have which is the strongest signal, which is the weakest signal. So, like that we have total 8 different signal strengths. Signal strength, and correspond to each signal strength there is some name. Then we have what type of this signal is this. So, we have total 8 such signals. So, the strongest signal is called as supply 1. This is for logic 1. I am representing this for logic 1. Similarly, you can obtain for the logic 0 also. For logic 1, the strongest signal is called supply 1, which is VDD. It will be called as SU1. I will come to that type later. Then supply 1, after that pull up 1, PU1 is the next signal strength. Then we have strong 1, these two are reverse. This is strong 1, this is pull up. Strong 1, ST1, then we have pull up 1, then large 1, weak 1, medium 1, small 1, then high impedance 1. Z stands for impedance. Okay. This is called as PU1, LA1, WE1, ME1, SM1 high Z1. These are the names. Okay. This is the strongest and this is weakest. Is high impedance. High impedance is nothing but open circuit. This is floating. Okay. So, the type is we can use this supply 1 for driving. This also you can use for driving. This you can use for storage. This you can driving. This is storage. This is storage, and this is high impedance. High impedance is floating just. Okay. So, the meaning of this one is, if the output of a circuit, some circuit is there, if this output is at supply 1 or strong 1 or pull 1, even if it is weak 1. So, in all these cases this can be used to drive the some other loads, some other circuit. If you want to drive this, we can use. Whereas, if you want to store as a logic 1, this large signal strength is also enough to store. Similarly, medium and even small also is enough to store as a logic 1. Okay. Whereas, high impedance is not enough. This will be almost like open circuit. Okay. So, these are the signal strengths. So, starting from supply 1, after that strong 1, pull up 1, large 1, weak 1, medium, small and high impedance. Suppose if I connect to RMOS, this is corresponding to logic 1. Similarly, we can write for the logic 0. This is input output. Suppose if the input levels are in the same order, this is supply strong, if these two are connected, then pull up large, small, weak, medium, small, then high impedance. The output is also high impedance. This is high impedance, output is also high impedance. If I apply to the RMOS circuit, if input is high impedance, output is also high impedance. Whereas, here this is the order that I have given. If I call this one as 1, 2, 3, 4, 5, 6, 7, 8. So, the levels 1 and 2, which is the supply 1 and strong 1, will give pull up. These two will gives to the pull up as the output. If I give the input as either supply 1 or strong 1, the output will be, because in RNMOS there will be resistance, there will be some voltage drop. So, because of that these two levels will comes to pull up. Okay. Similarly, this third level pull up will comes to weak. If I give the input as pull up, output will be weak. If I give input as, this is third level, fourth is fourth and fifth. That is, if I give the large and weak as the inputs, then you will get output as medium. And if I give this medium and 6 and 7, medium and small if I give, so you will get output as small. For high impedance. Okay. If I take the RNMOS circuit, the input and output levels, so the first two levels supply and strong will be reduced to pull up, and pull up and large, third and fourth will be reduced to weak, large and weak will be reduced to medium, and then medium and small will be reduced to small in case of RNMOS. So, these are about some signal strength. When the signal propagates through the resistive switches, the signal levels will be decreases. Okay. So, this is about this the signal strengths and the modeling of the CMOS circuits using switch level. Thank you.